right, let's go. Oh, first problem. So I wanted to give you your formula first. This is your general slicing method. Suppose a solid object extends from x equals a to x equals b, and the cross section of the solid perpendicular to the x-axis. It's got to be perpendicular to the x-axis. Has an area given by a function a that is integrable on the closed interval from a to b, and the volume of the solid is the integral from a to b of a of x, the area function, dx. Let's see. So here's an example. The volume of a parabolic cube. There's a parabolic cube. Now you know. Now the x and the y-axis are kind of funky. You would have to rotate that, take that counterclockwise about 135 degrees to get it to look like normal. I don't know why they didn't draw it in the right way, but shoot, it's better than my drawing would be. So it's saying that we have some function, some 1 minus x squared. Y equals 1 minus x squared. And we have this square that's making this parabolic cube. So as we move it, I mean, if you take this thing and you take it closer to the end of it, it's just going to be a smaller cube. See, I can't draw. I can't draw for shit. Dang it, I swore. Try not to swear. Yeah, so there would be some sort of square going on here. But notice the square is going to change size. It's going to get bigger and smaller depending upon what that value of x is. And the closer and closer that x value gets to 1, the smaller and smaller the area of that square will be. Now let's go down to our next picture that might help us out a little bit more. There's the slice. Since it's a square slice, it's talking about a parabolic cube. You hear cube, you know that all sides are the same. So we're trying to find the area of that square. And then we're going to go from x equals 0 all the way down to x equals 1. So the area of a square is just the base squared. But we're saying that our base is the function 1 minus x squared. So the area of our function is just 1 minus x squared. There's the base of the square. No matter where we go, it's 1 minus x squared. But since it's a square, we have to, believe it or not, you got to square it. So now we have our area function. Write that in, a of x. So we're going to use our volume. Our volume tells us we need an integral of our a of x dx, but we need to know what our a to b is. Well, since this problem, we're saying let R be a region in the first quadrant, bounded by the coordinate axes, and the curve y equals 1 minus x squared, a solid has a base R. That's the bottom part of it. And cross-sections through the solid perpendicular to the base and parallel to the y-axis are squares. It's telling you they're squares. Find the volume of the solid. So we already have our area function. It's 1 minus x squared squared. But now we need to know our a to b, our values of x that we're going to go through. But clearly it's going to start at x equals 0, and it goes up to x equals 1. So our a is 0, and our b is 1. Now that we're here, we can go through and we can just go find our volume. It's not a tough problem. This is about as simple as they get as far as the calculus part of it. In my personal opinion, the setting them up is the toughest part. The calculus afterwards is usually pretty mellow. So let's square all this up. We get 1 minus 2x squared plus x to the 4th dx. I'll let you figure out why that's true. And now we can go through and find our antiderivatives. There we are. From 0 to 1. Hey, zeros are the best, right? Because that means that second part, that big F of A just goes away. So now we have 1 minus 2/3 times 1 cubed plus 1/5 times 1 to the 5th minus 0 plus 0. Oh, that's nice. That's nice. So now it's just dealing with fractions again. So it's 1 minus 2/3 plus 1/5. So let's just get ourselves a common denominator. So that's going to be 15. So 15 times 1 is 15. 5 times 3 is 10. 3 times 1 is 3. So what do we got? 15 minus 10 is 5. 5 plus 3 is 8. And we ended up with 8 over 15 cubic units. We don't really use units in our math. You can deal with that when you do physics. So there's our first problem. I was going to do 2. But let's just keep them a problem at a time. So there's the volume of a parabolic cube. We'll come back. We'll do a parabolic hemisphere next. And then we'll start moving into what's called the disk method and the washer method. All right. Take it easy.